Okay. Again, thank you to be here for this lecture, the last lecture related to the PSO, particles World optimization algorithm, and as a part of the discrete identification. Discrete because we have seen that we are working stepwise, no? But of course, we can apply this algorithm also in the context of continuous. No? But anyway, if you think about the structure of the algorithm of the software, step by step recalls me the concept of the discretization. Not only in this sense. You remember the scheme or the problem which we have in such kind of algorithm. Let me switch on the lateral camera and let me show you what I intend, which is an effect of the discretization of the data, is the effect of the discretization of the algorithm somehow. Let me switch on the lateral camera so we go in depth on some particular aspects, and after that we can see what I intend with discrete and which kind of problems will appear. 1 second. Let me see how I can switch on the lateral camera. I don't understand how now. Here. Why doesn't work? Second. Now. Do you remember this scheme? Just to understand, I am considering just a problem in 1 dimension, because in 2 dimensions it's the same. Assuming that this is the mean. But of course, it's more difficult to be represented in a graph structure. Yeah, assuming that is the minimum. I don't know, x star. Of course, this is the minimum in an ideal situation in which I can represent the cost function, assuming this is the cost function, in continuous form. Let me say, roughly speaking, in a flat in the sense, in order to understand what I intend with the word flat. Look at this possible representation. Which is the real representation of the cost function in a microcontroller, in the computer somehow, because the computer represents everything in discrete form. To be a little bit more precise, should be also something a little bit more hard. Look, what I intend. Something like that, in order to understand just, in which not necessarily the minimum is localized in the analog minimum, in the continuous form minimum. It could be that because of the randomized structure of the PSO, the minimum which PSO will find is close to the minimum of the continuous function, but it's not exactly the minimum continuous, because we have many valley here, many valley. Excuse me, I have to stop a couple minutes and I come back. 1 second again. Okay, this means because of the discretization, let me say, of the procedure, in this case, I would like to say the discretization of the cost function, we have many valley we can understand. And it could be that the PSO, the algorithm, will find something close, but not exactly the minimum, because exactly, no, that the word exactly no meaning in the concept of discrete or discretization of functions or in general system. Let me show you this using the software of last time. Really take into consideration this kind of problems in, in when we apply in applications. Let me open again the MATLAB. And let me show, do you remember last time I already introduced this topic at the end, but let me repeat because it's extremely important theoretically, but not only theoretically. Look at this. This is exactly the main program of last time. I put it, yeah. I considered, let me say, a problem in 2 dimensions. Now we can see lower bound and upper bound with two variables, x1 and x2, for instance. But of course, you can put just one variable. We have to, how possible to say, reduce the dimension of the problem. But let me show in with two variables. Of course, take into consideration that this kind of problem to find let me say in a better minimum or maximum, it doesn't matter what we want to look for, is more evident, these errors, let me say, these numerical errors, but it's not only numerical error, it's connected with these multiple valley which we have again on the picture here. Even though theoretically the optimization problem is a convex one, because we have theoretically just one minimum in this case, the same consideration can be done for the maximum or the maxima. We can see that practically, the problem is not convex. In the sense, in the discrete form, we have many values. Look what happens. Now, let me consider in a system with two variables to be optimized, x1 and x2. Let me see what we have here. 10 is the population side, 10 particles, 10 birds. If I run, the function which must be optimized is this one. 2 dimensions, x1 and x2. The minimum is at point x1 equal 2, at point x2 equal 3. We can see that we have this value for x1 and x2 for reason of resolution. Nevertheless, the computer find 100, but it's not correct. Because it's 100 at x1 equal 2 and x3 equal 3. It's not the case. Yeah, equal 3. It's not the case. This is a numerical aspect. I can solve this, yeah, but I don't remember what I have to change, but it's clear that this is a numerical aspect. Let me copy this one. Look now what happens. I don't want to do now to speculate on the resolution of the computer and so on, but it's clear if you look that the minimum, which equals 100, is at x1 equal 2 and x2 equal 3. I will think how I can show you that it's not exactly 100, but now I don't have in mind. Probably have to put format long also when I calculate the value of the object function, but this is a technical problem. Let me show you one concept now. If I increase the number of particles, for instance, 1,000, of course, the algorithm take more time. This means needs more steps, because do you remember in this variation we don't have intermediate check. We don't have a stop criteria. We will run until the end. I will show you what I intend with this in a few minutes, because also this should be a little bit analyzed more in depth. Look at this. Now, let me run. Now, theoretically, and we can demonstrate, theoretically means statistically, these values should be close to 2 and 3. Why I say statistically? Because the statistical nature of the algorithm remains. This means if I do 10 tests, of course, we can realize that with 1,000 particles, we will find statistically the minimum closer and closer, let me say, to the values 2 and 3, which is the ideal minimum. Ideal means considering an ideal situation in which the cost function is represented in continuous form. It's not possible. Let me compare. Ah, stupid, I didn't copy. Okay, let me see. Okay, let me copy this. I hope that I copy. Let me see. Now I copied. Let me rerun the program using 10 because I forgot to copy with 10. It does not take much time. Yeah, we can see these two values. Yeah, we can see also optically that this value, the first value, for instance, is far away, more far away from 2 with respect to this one. Because here we have 1, it seems to be, yeah. And here we have, excuse me, here we have 1, here we have 0, no? Let me see here. The same here, it seems to be, but we can test exactly if you don't believe me. But of course, statistically, it seems to be from the first test, it seems to be correct. Let me see if I am able. No, it is. Let me see. It seems to be right what I am saying. Let me see. G best 1 minus this. Yeah, we can say that G best 1 is larger than the value. Of course, extremely small, but it's larger. This is related that probably we have two reasons. The resolution of the discretization of this in this context of the surface is extremely high, and not only. As I told you, this is more interesting in the concept of the algorithm. We have just 2 dimensions. We have just 2 dimensions. As I told you at the beginning, this kind of problem, the problem of the valley in the sense, valleys in the sense the approximation of the minimum is more evident for optimization problems with higher dimensions. We can understand a little bit why that. Let me. We can understand because there is theorems or results which demonstrate, it is intuitive also, that the precision, let me say the probability to find better, probability is better to speak about probability to find better solution is connected with the density of the particle. With respect, the density is always particle, let me say, divided the search space. Just a second, just a second. I remain online. Okay, okay. Excuse me again for this interruption. Yeah, and the probability to find better minimum or maximum or maxima, minima and maxima is related to the density. It's intuitive. You remember last time I told you if I were to find an object in this room, it is a search region. Of course, it's higher if we look with more people about this object instead of less. No, it's intuitive. There are results of this. There are results. Okay, this I think I clarify a little bit. Let me now, in this in this 10 minutes, 15 minutes, open an interesting file, more, I don't want to say complex, because we will see that the structure of the software is exactly the same. Therefore, it's important, in my opinion, this lecture, because it's relatively easy, but it's the basic structure of the PSO. Now, in our lab, we implemented different variations of PSO, also complex, which considers, for instance, more than one G best. What is the meaning? The meaning is instead of one, let me say, dictator. It's not a dictator, because we have a P best, which represents the population, and from the population we elect the best element. In this sense, the election is this selection. The sense is the selection in accordance. We select the best in accordance with the results. It's nevertheless is democratic, but based on the meritocracy. We can consider also more than one G best with some priority, the best, the second best, the third best. We have also this variation. In this sense, please consider also to apply this algorithm in the context of some possible variation, which we can discuss not in the lecture, because sometimes it's not so easy to be understood, but in the context of the project. Why this variation? For instance, this variation here. The idea is always to balance between exploration. You remember, I told you I think I showed you an animation about that. Exploration, when we are looking for, let me say, everywhere, and exploitation, which then let me say, in the second phase, we can concentrate, the algorithm will concentrate on in 2 or 3 valley or minima, in this case minima, at the end to focalize in one of them. About that also, there is literature, and the variation some variations is based on this concept here, in order to try to optimize these 2 phases. Of course, everything is a little bit heuristic. And again, we applied also different variation, including adaptive. Do you remember this C1 and C2, these acceleration parameters? Always meet the idea to adapt exploration and exploitation. We implemented this. This means in a possible project in which we can include the PSO, or we can just consider PSO in an identification problem, we can go in depth really in this kind of different PSO structures. For instance, we can work without GBEST in an anarchic form. It's not exactly to say anarchic, but we can say in the sense that we don't have the boss, which indicate the best direction. GBEST is more oriented to the exploitation, because indicate a direction oriented the swarm. You remember that I told you last time. And without GBEST, of course, we emphasize more the exploration. Now, in which kind of problem we can consider different variation? This is an open problem, but of course, let me say, we can discuss in this sense. I mean, if the problem, let me just give you an idea. If the optimization problem is quite flat, meaning is let me show you what I intend. But not complex, of course, something like that. Of course, here it seems to be intuitive to think that the more possible suitable algorithm is more anarchic, because sometimes it's useful to prolong the exploration in order to look where this is, because it's not clear where the minimum is. This means if I involve GBEST, of course, it could be that I will find something like here and not here, or in this sense. But in any case, it's an open problem. When we have to finish with the exploration, when the sense when or when we have to start with the exploitation phase. And in this sense, again, the variations are oriented to solve this kind of problem. About the last thing before showing you the new software, let me print plot fminplot. Fminplot, let me show where fminplot is. Fminplot is defined at line 15 of the main program, and this line is the line which allows to define. You remember last time I told you to define a vector with infinite dimension. Infinite doesn't make sense in the sense until overflow of the machine. The meaning is this that I can put, the overflow is correct, without dimension the sense. No? I don't fix the dimension of this vector. This means if I plot this vector, and in this vector I put all minima. Let me show you what I intend. You can see, it's important also this aspect here technically. Here, at line 203, you can see here that in fminplot, I store the fminplot which I had before, and I add in the sense I put in the last position of the vector the new minimum. Do you remember last time I clarified fmin and so on? This means I increase always at each step the dimension of fminplot. I increase the value, I increase this vector in which I store the minima which I find or which I found at each step. Look how it looks like. You can see that starting from the value which I found in initialization, I will go down, why down? Because we are looking for the minimum. No? Very quickly, let me show you a little bit. And then starting from 40, I am almost at 100. Here, the resolution does not allow to distinguish. It's not exactly 100. I already discussed. What is the meaning? Why I'm explaining this aspect now? The reason is it could be useful, is useful, in particular when we are working online, that we stop the algorithm somewhere before finishing the iteration. I mean, you can see that starting for more or less 40, a little bit more than 40, we don't have progresses. Now, how it is possible to know 40? Of course, we don't know when this happens, but we can put some intermediate check or the checking in order to say, please pay attention now. The improvement of the minimum is not relevant, and we can stop. This is a possible idea, but of course the risk is if it's we will stop here. Here, for starting from I don't know, 2 or the 3, the second step. I don't know what. Let me see. Yeah, exactly. The second step until step number 17, we don't have variation. This means very often this is not enough just to say we don't have variation, we will stop. And therefore, we have to think about some combined criteria in order to avoid to stop too early. But in the meantime, we have to guarantee that after yeah, I have seen 40, but we can see that we need a little bit more. No, but anyway, we can see sometimes, no, uh, sometimes we can be satisfied with almost 40. How possible? Again, less variation, but also the value which we have. Okay, but also now I know that the minimum is 100. If I don't know, yeah, this is a big problem, but very often we know more or less which kind of current voltage or population which we're working, which we're waiting for, or we know when this value which we're looking for is nevertheless enough. Or we have also other criteria, no? Other criteria. Uh, this picture last time I sketched, now I told you more in depth. Okay, I told you more in depth. Let me now open the file of the project. You can find this file in my study. The name is PSO fitting. Let me, otherwise it's not polite. I continue 10 minutes. I already told you that I have to stop, but I informed also the people of the next meeting that I will reach them a little bit later. Look at this. The structure of the program, the structure of the software is exactly as before. Of course, in the real project, is in a project related to it was in a project together with Professor Georgiadis, OptiRope, optimization and robotics. Is again the problem to find velocity. Do you remember I told you at the beginning, translational velocity and rotational velocity of a robot. This was in a pilot software at the beginning, but I simplified a little bit for you. But look, we have nevertheless real data. Now I will try to explain, but believe me, the structure of the software is exactly the same. Of course, when we applied in the lab, we had it's more complicated because we did something different, something more, and we realized just one software in order to optimize also the software itself. Optimize the software itself means to minimize. Let me so roughly speaking, I am not expert. Vincent is a very good programmer in order to minimize the line of the programs, in order to minimize external calls, everything which you probably know better than me. Here, didactically, nevertheless, in my opinion, is effective to separate main program with the let me say with the function which is the function to be optimized. But of course, just didactically, I think. And also inside the main program, we optimize some loops and so on, but not I, because I'm not so expert. But conceptually, we started with this. No? We started with this. Look, this recalls Benedict, no? Is the data which we measured. Now I told you in the real experimental setup. Let me show you what this symbol, we can see a symbol software realizes why we use this. We increase the complexity in the sense we improve the model, and I show you what I intend with the model. And then, of course, at the end, we realize something different, but conceptually the same. Let me start as in the first example with the definition of the cost function, because the idea is to minimize something. And yeah, I would like to explain why, what we minimize and why. To minimize, we can understand. To minimize, but I show you a little bit better. But in any case, what we minimize? Again, isn't a function because we have the main program, which is exactly the same. I will scroll down later. Is exactly the same what I tried to clarify in the first example. Look, I commented these two lines because at the beginning, probably was another lecture in which I put some artificial value for I don't remember for what word used. In any case, look, after the command global, I define two data x and y. Let me see. I don't remember. I think x. Let me think because I don't remember exactly. I think y is the roughness, which we measured, and x is the position just in one dimension when we have this roughness. Of course, the problem is more, consists of more dimension, but let me start with this, because we started also analyzing this kind of data. Basically, why the output of the measurements and the roughness, we used englosmeter uh, with the light, with the reflection of the light to look at which position uh, we have, basically to say we have in a position, we localize this position and we measure the roughness. Consider this an instrument is glossmeter, not expert in measurements, which measure the reflection. That means if the light is, we have a high diffusion of the reflection of the light, we have a very flat surface, very small roughness. Otherwise, but I'm not expert about that. Otherwise, we have, and the instrument is able to give a value about this roughness. But I am not expert here. But X data and Y data are called in the main program. The structure you can see exactly the same. We are considering the first approach 3 parameters to be optimized. I will tell you which kind of parameter. We can see also a particular value which recall as something real, no? 10 up to -4 and so on. 3 parameters, of course. Again, in this form here, we didn't C1 on K1. In some lectures, we have a C1 instead of K1. We have a C2 instead of K2. We fixed here. In more advanced software, we included or we change these two parameters in adaptive form to balance exploitation. Exactly. Let me see. Yeah, here. We can see it. I define globally these two variable, even though now I made mistake before. We can see that I don't use because it's here. Yeah, excuse me, I made mistake before. I told you that I didn't use, but we can see that I lowered the real value saved in this MAT file. Probably you know a little bit MATLAB. A MAT file are file which I can save data, real data from external. Real data, also artificial data in general. This rest of the software, is exactly the same. The unique difference is that we have 3 parameters instead of 2. What this software does, if you look at the software, is exactly the same. Of course, the cost function to be optimized is not a parable, but this is the point here in the concept of the project. This is a simple exponential function which should fit the measurements, basically roughness as a function of x dimension. Of course, in the next step, we consider also x and y dimension because we have to optimize the roughness of a surface. This means that we don't have just one dimension x, we have a dimension also y. But just to show you in an easy example, we are considering just in one dimension, and a relative easy, but not so easy function to be optimized, an exponential function. What we optimize? We optimize, this is the regressor which we are considering, an exponential function which depends on x, with just three parameters. The amplitude of the exponential function, the exponent of the exponential function, we can see which is multiplied by x data. Why x data? Okay, now I remember. Because in a Benefile, MIT, we have save with x and y data. Again, this no meaning, but x data and y data are inside, now I remember, the Benefile. I show you what I intend in 1 second. And then the optimization consists of minimizing the least square, for instance, in this case, and for instance, between the roughness measurements and, let me say, the regressor. Basically, I will find the best x1, x2, and x3 in accordance with the structure of the regressor, which minimizes, in accordance to the least square method, my cost function defined as I express. Basically, the least square, you can see from here. The sum of what at this point at each y data, I will subtract the corresponding value of the, let me say, regressor, which I considered as approximating function. Now, the problem is why this regressor and not another one, wavelets or polynomial, and why just three parameters? Okay, this is a big problem in the optimization. In the course of optimization last time, do you remember last semester I told you about this R square adjusted? I don't have time to tell you here because this is a problem, is in a concept, is in an aspect which must be introduced in a real optimization course, which I already did. But anyway, in the project with me, we can also reconsider our knowledge in optimization and to apply. I mean, we have methods, and I introduced one of the most used in the last semester, which we can see which kind of regressor, could be polynomial, could be exponential, but how many exponential? This means how many coefficients, could be wavelets, could be arcotangent, could be everything. We have methods to choose which one is, let me say, the best in accordance to criteria, or at least one criterion. R square adjusted is one of them. Assuming that we know, but anyway, I don't have time. That's really very, very in depth. It is very in depth, this aspect in the optimization. Once we define again the problem with the problem of the fitting, the idea, the problem consists again to find parameters. In this case, three parameters. In this case, without thinking why 3 is not 4 or why this regressor. Because of course I see why this element here, which move, let me say, up and down the regressor. Intuitively, I would like to put it, because eventually the PSO will find something close to 0. It's in general, let me say, once we say, thanks to some criteria, that the exponential function with one exponent is the best. This can be done, for instance, with the using the R square adjusted or different criteria in optimization. Of course, this is the general structure, because I have to calculate the amplitude of the exponential function. I have to calculate the exponent of the exponential function and the level of the exponential function. Again, we can see I commend my original file. This means also in real projects, we can use what I told you last time. The structure of this of the software is exactly the same. The unique difference I define as global X data and Y data, which are not this one, but is defined in this MAT file. Let me run. Let me see if I forgot to comment something. No, we can see that is exactly the same. Here I didn't put this infinite vector, but you can do that at home. Exactly in the same format. No, I don't have it. In the same format which I already explained also today again. Let me run. This is the final results of the optimization. Of course, it seems a little bit strange. In fact, we improve a lot let me say the approximate. The idea is to approximate this data with a function in this phase of the project. Of course, we change the regressor basically, and the regressor which is starting from 0 is going up as a complex really regressor that is going up, take information here and then is going down. Consists of more than one exponential functions. I have, if you want, I can upload. The difference is just, let me see if I have. The difference is just the definition of the regressor. The problem does not change. Let me see if I find this, why I conclude. This was done with the R-square adjusted. Let me see if I find. I don't find quickly, but I will look for you. Here I have just a symbol. But I have it because we have all software at the end is relatively complex, because this is just of a part of the project. At the end, we have to calculate we calculated the velocity, translational and rotational velocity of the robot. 1 second, if I find, I will show you a more complex, but it's not necessary because you can. Let me see 1 second. It could be they have. No, I don't have. Okay, it does not matter. I will find. In any case, the project is not active now. We concluded is in a relative old. It's not old, but is in a project which we concluded 3 years ago. This was in a preliminary analysis of the characteristic of the material. Basically, the idea is to find in a surface which fits the roughness as a function of omega, rotational velocity, and translational velocity. It's not the case which I presented today. When we have this problem, which is a problem in optimization in terms of fitting, first PSO, let me say, method. Then we have another PSO that look for the minimum of this surface. I mean, first PSO is an optimization problem because it's the best surface in 2 dimensions, omega and v, translational velocity v, translational velocity and omega, rotational velocity, which fits the surface, the roughness function. Then another optimization problem to find omega and v, which minimizes the surface which fits the roughness as a function of omega and v. I have a very think, but in the lecture, I think this is a little bit enough for this aspect here. Again, this project is not more active, therefore, but we can do in the same way these 2 steps also in another context. We did something similar in Rolls-Royce. First of all, PSO to realize in a cost function which fits the measurement data, because everything came from the measured data. And then we find in that case was IQ and ID current in synchromotor. We have in DQ transformation 2 currents, and we find these 2 currents which minimizes this function. I don't remember what is the power function, something like that, to minimize the consume the losses. Okay. If I have a question, I'm here to answer your question. Otherwise, as I told you, I have to move to another meeting next week in hybrid. This means I will be present in Lüneburg. We will attack another problem in the context of the discrete optimization, but more related to the dynamical systems. And then after that, at the end, I will dedicate, I think, 2 or 3 lectures again. We will start with the control, with discrete control. And we will go ahead also. You remember, I told you my idea is to tell you about also model predictive control because it's in a discrete form, but just at the end. Okay, if you have questions, I'm here to answer the question related to the topic or the aspects which I consider today. Otherwise, the material is in my study. In any time we can discuss about that. It's not so, in particular during if you want to go, if you want to apply, or if you want to analyze in your project the PSO, could be also important to combine a PSO with other methods. No? Vincent knows exactly what I intend because he already combined PSO with model predictive control. In the sense, with Vincent, we can go ahead with this, or we can change, considering other aspect of discrete control. We can do. Okay, questions? If no, I would like to stop now the recording.